Hello, let's go through another problem from the 2024 British Informatics Olympiad. This time, let's go through the scary problem. As usual, you can pause and read this. I'll link it in the description as well. But I will explain it myself. Well, this time it won't be on a whiteboard. This time it'll be using this animation that I have. This animation was actually made available to the contestants in the contest, although without these analysis tools that we'll be using later on, because they may give you some hints. So what's the problem? The problem's on this grid. We have a grid, and some of the cells in the grid are occupied, and the rest of the cells in the grid are free. So ignore the colors for a minute here. We just have a grid with these circles representing occupied cells, and the empty cells are empty cells. And so what can we do on the grid? Well, we can make two types of operations. So one is we take a pair of adjacent occupied cells, so like these, where adjacent means two cells sharing an edge, and we can annihilate them like this. Just make them both disappear. That's one move. And the other move is we take a cell with an occupied cell with no other adjacent occupied cells. So like this one, because none of the four cells adjacent to it are occupied. And we expand this cell, which means we remove this cell and fill the four surrounding cells, like this. So like I said, ignore the colors for now. Well, actually, I can explain what the colors mean. The colors just mean that the blue cells can be expanded, and the green cells can be annihilated. So this cell can be annihilated with two options here. So when I press it, it lights up as red, and then I can choose the partner I pick with it. Yeah, so green can be annihilated, blue can be expanded. These are just visual effects, visual aid. So those are the moves we can make. We can have cells as well on the edge of the board, but those cells, obviously, we can't expand, and we might not be able to annihilate. So in this case, we can't make any moves on this cell. So that's why it's gray. So the problem is asking us, given a grid layout, given an initial grid layout, we need to find a sequence of moves which at the end minimizes the number of cells that are still occupied on the board. So we want to wipe this grid as clean as possible. We want to leave as few cells as possible on the grid. So in this case, you might start, just annihilating pairs of cells, stuff like that, and then you reach this case, and well, you're not really sure what to do here, because if you expand a cell, that deletes one cell, but it creates four more, and that feels like it usually won't pay off unless it's a very specific situation, right, where you can annihilate a lot of cells after that. So initially, it feels like a tricky problem, because it feels like expanding is not often the best move. But say in this case, for example, you do want to expand, and you have to expand a specific cell. It should be this one, right? So that then you can annihilate these four pairs, and then just leave this pair to annihilate. So initial thoughts, this problem feels difficult. One more constraint before we dive into the solution is that not all the cells on the grid can be full. Oh, and obviously I have to tell you the size of the grid as well. The grid is massive. The grid is 1,024 cells by 1,024 cells, always the same. So it's always that dimensions. Well, we don't have it that big a grid here, just because, well, this is already pretty big. So for manually playing with the grid. For those purposes, this is pretty big. So the grid will be 1,024 by 1,024, and the number of cells occupied will be at most, I think, 256. So yeah, that's here. So the grid is 1024 by 1024, and there are at most 256 occupied cells on the grid at the beginning. And also two more constraints. So one that helps you, the outer 2 layers on the grid will never have cells in them. So if I take a look at the maximum number of cells that could be filled on this grid, these 2 layers on the outside will always be empty. So, I mean, this is a 10 by 10 grid, but the same on the 1024 by 1024 grid. So the outer 2 layers will be empty. And the last thing in the problem is that you should use at most 1,000,000 moves, where we have those 2 types of moves, annihilation and expanding, that we mentioned earlier. You should use at most 1,000,000 moves to reach the state that you want to reach. And actually, you should have no more moves once you've reached the minimum, but that's just a detail. So that's the entirety of the problem, I think. So now let's get into solving it. So what's the main initial observation in this problem? Well, if we have something like this with a few cells far away from each other on the board, we don't really know what to do here. At the moment, we have no idea whether this is the optimal position, whether we should stop, or whether we should somehow keep going and start expanding these things. So the first observation is to do with that. So let's take a look at just one of these cells, right? Just one cell. Let's look at this one over here. Well, actually, I'll just draw on a smaller board. Let's look at one cell. There may be other cells on the grid, but let's just look at this specific one. If it has nothing around it, the only thing we can do to it is expand it. And then, well, what can we do now? Well, we have to expand one of the other sides again. So let's just try expanding this. And now we've reached an interesting position because all of these cells have turned green, because we can cancel them in pairs. We can annihilate them. So we can annihilate these 6 cells like this. And now we have remaining 1 cell again. So we started with 1 cell, we ended with 1 cell in 5 moves, but the cells moved. The cells moved 2 spaces to the right, from this space to this space. So I can try undoing that so you can see. So we started here and we finished here with 5 moves. And so we can do this pretty much wherever we want, as long as we have sufficient space. So what does sufficient space mean? Well, we need space around the initial cell to make the initial split. So I need the 4 surrounding cells to be empty. Then in the direction that we're moving, right, in this case we're moving right, we need the 4 surrounding cells around that one to be empty as well. Obviously the one to the left will be empty because that's where we started. But so we need this cell, and this cell to also be empty. So we can move this cell that we had here initially 2 spaces to the right. If all of these cells that we have here are empty, including this one as well. We can move it two spaces to the right. So if we start here, and if all of these cells are empty, and we started here, then we can move to this. We can move 2 spaces to the right. This isn't only to the right, obviously. We can do it in any direction. Let's say we take a bigger board. We can move this cell down if we want to. We can do this, this, and then cancel these. And now we've moved it 2 slots down. 2 spaces down. So we can move cells with sufficient space, but we'll ignore that for now. We can move cells 2 spaces in any direction. And we can do this with most cells, right? So let's say that the board was really strung out. Let's say that the board was really strung out, really sparse. There weren't many cells on it. Well, now it's time to look at these analysis tools. So if I put these on, you'll see that now I can move this cell, for example, 2 spaces to the right, or 2 spaces down, or 2 to the left, or 2 up. So I can move it to any of these slots. Also, I can move it down twice, right, to this space. So I can move it to a lot of places. So if I wanted to cancel this cell with another cell, I can move it and cancel it with this cell, right? So I obviously, since I'm moving 2 spaces at a time, if we look at this chessboard coloring that we've got here with, well, let's just call them black cells and white cells, I obviously can't annihilate a black cell with a black cell or a white cell with a white cell. But with sufficient space, I can annihilate a black cell, any black cell with any white cell. So for example, if I want to annihilate this black cell with this white cell, well, in this case, you just annihilate this first, right? You have this black-white pair. You just cancel them. Now you want to annihilate another pair. You have this cell and this cell. Well, you'd bring this cell down or this cell up. So let's just say bringing this one down. We do this. And now we've brought it down 2 spaces, and now we can annihilate them. So we can move, the fact that we can move occupied cells with jumps of distance 2 means that we can essentially annihilate pairs of cells. If we have sufficient space, we can annihilate any black and white pair. We can always annihilate a black and white pair. Okay, so another example of what we could do is we could take, say, these cells and see what happens here. So we have 2 black cells and 2 white cells. And again, we can annihilate all of these. Let's say we can move this black cell 2 spots to the right, and then annihilate this pair, and then move this black cell 2 spots to the right as well. And again, or we can move this white cell 2 spots to the left now, and then we annihilate these. So you start to see the kind of things we can do now with this move. So this is really useful. So if we have sufficient space, we can always cancel a pair of black and white cells. We can cancel a black cell with a white cell by bringing them close together. Now, if we go back to the problem and look at the constraints, remember we mentioned that the grid is big. The grid is very big. It's 1024 by 1024 squares. It's always the same size. And the number of cells is, well, moderately big, but quite small compared to that. It's 256 at most. So this grid is going to be pretty sparse. Even if all the occupied cells in the grid, in the starting grid, were all in one column, we'd have at most a quarter of that column occupied. So that means our starting grid is pretty sparse. So we will have quite a lot of space. And the fact that we have these 2 outer layers on our grid that always start out as empty means that we won't have cells like this, which we can't move at all, because they're on a wall and we'll never be able to move them. We won't have that case. So we will have space, just to say that intuitively. We will have space to make at least some moves on certain black cells, on certain white cells. So we'll get into exactly how we'll cancel pairs, how we'll find a pair to cancel a bit later on. But for now, let's just assume that we have sufficient space on the board to always be able to take a pair of cells, a black cell and a white cell, and bring them together and cancel them. So let's say we can always do that. Let's make that assumption for a minute. So what does that mean? Well, that means if we have some grid layout of black and white cells, let me just move these out of the outer 2 layers, just so it's a valid starting setup. Yeah, so we have some black cells and some white cells. In this case, we have 5 black cells and 4 white cells. And we've made an assumption, that a fairly reasonable sounding assumption, that we can always take a black cell and a white cell and bring them together and cancel them. We don't care how at the moment, but let's say we can. What does that mean? Well, that means in this case, since we have 5 black cells and 4 white cells, as it says down here, we can start cancelling pairs, right? So we can say cancel this pair, then we'll have 4 black cells and 3 white cells. Then we can cancel another pair, let's say this pair. The specifics of how we cancel it don't matter. In reality, we'll be moving this to that, let's say, and then cancelling the pair. But we don't care about that. Let's just say we're cancelling. Now we have 3 black cells and 2 white cells, and we can keep going. We can keep cancelling pairs of cells, so a white with a black and a white with a black, until one of the colors runs out, right? So if we started with 5 black cells and 4 white cells, we can keep cancelling pairs until we have 1 black cell and 0 white cells. So that's one thing we can do. So we can cancel cells until we have only 1 color of cells remaining. And then what can we do? Well, in this case, maybe this is optimal. But we could have a lot of black cells, let's say, and not many white cells in the starting setup. So we have 7 blacks and 2 whites. So let's say we cancel 2 pairs, and now we only have black cells left. Is this optimal? Well, this is not, because we have another way. We have a way of generating white cells from black cells, right? We can expand this cell and one of the cells, and instead of having 5 black cells like we do now, we'll lose 1 black cell, but we'll gain 4 white cells. So now we have 4 and 4. And now we can just cancel pairs. And this last pair as well. Last pair as well. So what did we just do? Well, if we have 5 cells of one color, we can expand one of them, and then we'll get 4 cells of that color and 4 cells of the other color, and we can cancel them in pairs because we've already made the assumption that we can do that, to eliminate all 5 of those starting cells. So if we have 5 cells of one color, we can take them all away. We can erase them. So now we're starting to get an idea of how to narrow down the number of cells. We haven't proved anything really, but if we start with some layout, we can cancel pairs of black and white cells until we only have 1 color of cells remaining. Then let's say we have 123 white cells remaining. Well, we can cancel those in groups of 5 by expanding one of the 5 cells and then pairing them up and annihilating them in pairs. And so we can cancel groups of 5 of those 123 white cells until we only have 3 white cells remaining. So we always have a way to get the grid into a state where we have strictly fewer than 5 cells remaining and they're all of one color, because otherwise we could cancel them. So what do we do once we have that? So obviously, if the state is that we have 0 cells remaining of that color, then that's obviously optimal, because we can't do better than that. So there are the other options are we have 1 cell, we have 2 cells, we have 3 cells, or we have 4 cells, all of the same color. So let's go through those one at a time. So actually, I'll argue that if we have 1 cell remaining, that is optimal. We couldn't have done better than this 1 cell. And same for 2. If we have 2 cells of the same color remaining, because if they were different colors, we could cancel them. If we have 2 cells of the same color remaining, that's the best we could have done. Not even the best that we can. I'm not even saying that it's the best we can do from this position. It's the best that we could have done from the starting position. If we have 3 or 4 cells, however, we can still do better. Let's say we have 4 cells. We can still, well, we can't cancel anything if they're all the same color, but we can still expand one of them and then cancel 3 pairs. So let's say that one, and then this pair. Again, I don't care at the moment how exactly we're canceling. So if we had 4 cells, we end up with 1 cell. We can end up with 1 cell. If we had 4 of the same color, we can end up with 1 of the same color. Yeah, 1 of that color. Wait, no, 1 of the opposite color. Sorry. if we have 3 of the same color, let's say we have these 3, again, we can expand one of them, cancel 2 pairs, and end up with 2 of the opposite color. So if we have 4 of one color, we can change them to 1 of the opposite color. If we have 3 of one color, we can change them to 2 of the opposite color. So yeah, now we know that even if we have 4 or 3 cells left, we can get that down to 1 or 2 cells. And I've claimed that that's optimal. So we now know that we can take any state on this grid, any state, as long as it satisfies the constraints that we're given, and get it down to 0, 1, or 2 cells, all of the same color. If they're 2 cells, they're the same color. We can always do that. And I claim that whichever one of those we can reach, that'll be optimal. And I can argue that now. Why will that be optimal? Oh, but before I do that, we now see that we have a game plan. Because if we show that this is optimal, and we know how to reach this, all that's left is working out the bit that we've sort of left out, how to pair up cells. How do you pair up cells? And cancel them, annihilate them in pairs. So how do we show that 0, 1, and 2 are optimal? Well, we obviously know that 0 is optimal. If we don't have any cells left, we couldn't have done better than that, because that is the best state in the game. So what if we have 1 cell remaining? Why is that optimal? Well, this is where we can do some clever thinking. By looking at the 2 types of moves that we have, right? So specifically, let's look at how many of each cell we have, how many white cells and how many black cells we have, and let's look at the difference between those 2. And let's try and find an invariant. So we have 2 types of moves that could possibly change the difference between the number of white cells and the number of black cells. So this move, the annihilation move, doesn't change that difference, because in this case we have, let's look at this number down here. In this case we have 1 white cell, 2 black cells, and so the difference between that is -1. The sign difference. So if we annihilate these 2, we lose 1 white cell, but we lose 1 black cell, so the difference stays the same. So the difference stays the same under annihilation. Now let's look at the other type of move that we have, expanding. If we expand this cell, we lose 1 black cell and we gain 4 white cells. So in this case, we'll lose this 1 and we'll get -1 here and +4 here. So in the difference, that'll be a +5. So the difference went from -1 to 4. We added 5 to the difference. Similarly, if we started with a white cell and expanded that, then we'd lose a white cell, we'd lose 1 of the white cells, and gain 4 black cells. And so that would be a -5 on the difference. So here it goes back from 4 to -1. So expanding changes the difference by multiples of 5. It can add 5 or subtract 5. And annihilation doesn't change the difference. So that means that this number down here, the difference modulo 5, will always be the same. No matter what moves we make on a board, the difference modulo 5 will stay the same. So now we can use that to argue our point, which is that if we have 1 cell remaining, the difference modulo 5 is either 1 or 4, depending on whether this cell is black or white, because a black cell is essentially -1. So in this case it's 4, but it's either 1 or 4. The difference modulo 5 is either 1 or 4. Whatever that is, let's say it's 4 in this case, that means that value is the same in the starting position of the grid, right? That value is the same in the starting position because that number doesn't change. And we couldn't have done better than this, because since that value doesn't change, that value could never hit 0 from that starting position. If you started from that starting position where this difference modulo 5 is 4, you couldn't make a series of moves to change this number. So you couldn't make some moves to change this to a 0. And you need the difference between the number of cells modulo 5 to be 0 if you want an empty grid. So we've shown that if somehow we've reached a state with only one cell remaining, we couldn't have possibly reached a state with no cells remaining from the same starting position. And similarly, you can make a very similar argument to say that if you have two cells of the same color remaining, then this difference modulo 5 is either 3 or 2, depending on what color that is. And you couldn't have possibly done better than that from the starting position because, again, the starting position would have had the same value, the same difference modulo 5. And if you wanted to do better than this, you'd either have to have 1 or 0 cells in the final position, and that would require you to have a 0, a 1, or a 4 written here, but you have a 2 or a 3. So this is the best you can do. Okay. So now we've shown that whatever starting position we have, we can always reach either 0, 1, or 2 cells, and that will be optimal. So now all that's left is doing it, which might actually be the tricky part. But that now we've done a lot of the thinking based on the big ideas. Now we need to look at the details and try and get a way to do this. So what are the main things that we have to solve right now? What are the main issues we have? Let's go quickly back over the main algorithm, right? The main idea. We're starting with some starting grid, and we start cancelling pairs of cells of the same color. So that's one question. How do we find a pair of cells of the same color to cancel? Because that might be tricky, right? Sometimes you might have to do something very specific. If you have, let's say, this kind of grid, this sort of grid, then you can't move this cell to cancel with this cell, because you can't move this cell down because you need this cell to be empty to do that. You can't move it right because you'd need this cell to be empty to do that. So you have to work from the outsides of this line, of these chains. So you'd have to move this one down. So you can't just take some random pair of cells and try and cancel them, because in this case, you cannot move this cell, and you cannot move this cell, and you cannot move this cell. So that's one question. How do we cancel pairs of cells? And the second question, so that's the start of the algorithm, right? We cancel pairs of cells until we only have one color remaining. Let's say we only have one color remaining. Let's say it's all these cells. Now, what do we do if we have one color remaining? Well, if we have at most 2 cells, we stop, but otherwise we need to expand one of the cells, right? So that's the other problem. How do we expand a cell? How do we find a cell to expand? Will that always exist? Well, that's a much easier problem, actually, because, well, any of these cells can be expanded. Because what do you need to be expanded? You need all your surrounding cells to be free. But since we only have cells of one color, all of each of their surrounding cells will be free. So we can expand any of these cells. So that's fine. That's not the issue. And again, now we need to start cancelling pairs. So cancelling pairs is the thing we need to do. How do we always find a pair to cancel? In this case, we'd somehow cancel these two. So that's the thing we have to think of now. This feels like it shouldn't be difficult, because each case you look at, there is an obvious pair you can cancel. But we need somehow to do this in the general way, in a general case, and also to keep the number of moves under 1 million, because 1 million might sound like a lot, but this is a pretty big grid. The number of cells isn't too small, and if they're pretty spread out, we'll need a lot of moves to get them to each other, especially because it takes 5 moves to do one jump of 2 squares. So we do need to think about that constraint as well. So to cancel pairs, this is what I do. I take the lowest white cell and the lowest black cell on the grid. Obviously, we have at least one of each, because otherwise we can't cancel pairs. We have to do something else. So let's take the lowest white cell and the lowest black cell on the grid. And let's take whichever one's lower, so in this case it's the white cell, and leave that where it is, and try and get the other one to that cell. So in this case, let's try and bring this black cell to this white cell. So since this is the lowest white cell and it's lower than the lowest black cell, it's the lowest cell in the grid, right? Well, it could be tied with other cells, but it's the lowest cell in the grid. And this is the lowest black cell, so we want to get this black cell to this white cell. So let's remove this cell for a minute. So we want to get this cell to this cell. So in this case, it's already on a row where it could reach this cell. So we just need to move it right. So let's just move it right. Once, twice, and now we just cancel them. So that was simple enough. We just moved it right twice and we canceled them. So if it was a bit higher up, say if this was the arrangement, so the lowest white cell is still this one, the lowest black cell is either of these two. Let's just say we choose this one. We need to move it down first because it's too high. And now we can move it right in the same way that we did earlier. So the useful thing about choosing the lowest black cell to try and move to the lowest white cell, well, we're not moving the white cells, but since we have the lowest black cell and we're only moving it down, well, we're moving it down, right? So no other black cells can get in your way when you're moving it down. That's the key idea here, is that no other black cells can get in your way because you're trying to move down, and if some black cell gets in your way when you're moving down, that means it was lower than you. It was strictly lower than you. So this wasn't the lowest black cell, so we picked the wrong cell. So if we pick the lowest black cell, these two cells, the two cells below to the left and below to the right will be free. So we can always move it down because these three black cells are the only three black cells we need to be free to move this cell down. Well, we also need these four white cells to be free, but we can talk about that now. So what if this cell is blocked? What if we just can't move it down? We just can't move it down because this cell is blocked. Well, in that case, why not just annihilate these two? Our aim wasn't necessarily just to annihilate this cell with specifically the lowest white cell. That's just what we're trying to do. But if we reach another white cell on the way, we might as well annihilate the pair. We can just annihilate that pair instead. So now we have an idea of what we're doing. We take the lowest black cell, we start moving it down until it's low enough, until it's at least on the row before the lowest white cell. Then we start moving either right or left until it's next to the lowest white cell, and then we annihilate the pair. But on the way, if we cannot make a specific move, if we cannot make a certain move, it must be because we have a white cell next to the black cell. And in that case, we can just annihilate that pair instead. So if we have a white cell on the way somewhere, let's say we have a white cell here, we need to move this down to get to this cell, right? We move this down, and now we want to move it right, but this cell's in the way. Well, let's just annihilate them. So that's what we're going to do. Again, if the white cell had been here, we would have done the same. We move it down. Now we want to move it right, but we can't expand it, so we just annihilate them. So that's what we're doing. There is one issue that could arise here, and that is this case. Something like this, where we have this cell, we don't need to move it down because we're already low enough to annihilate with the lowest white cell. We want to move it right. So to move this right, we need these three cells all to be free. This cell will definitely be free because this was the lowest black cell, but these two cells over here might not be free. So that's the issue. That's the issue. If we haven't made any down moves at all, then moving left or right, we might hit other black cells, and that's an issue. So how do we fix that issue? I mean, in this case, we could just move down anyway, move down to this cell and move right. But this white cell could have just been this one, right? It could have been on the same row as the black cell. And in that case, we can't move down, because then, we'd have to move back up. That might be fine, but that complicates things. How do we want to do this? Because this could be pretty low down, right? This whole thing could be happening down here. And so if we move down, we could end up on the edge of the board and be unable to move anymore. So we don't want to have that issue. So this is what we'll do. Let's assume that instead of the bottom 2 rows in the grid, the bottom 2 rows in the entire grid being free, we have the bottom 4 rows in the entire grid free. So we've said earlier that we have 2 rows surrounding the grid entirely free. At the bottom, let's assume the bottom 4 rows are free. And we can easily make this happen at the beginning of the game, just by moving everything up in a specific way. But we'll talk about that later. It's not too difficult. So the main idea is we can somehow make the bottom 4 rows in the grid free. If we've done that, now what can we do? If we're trying to annihilate a certain pair, let's say before we cancel a pair, before we annihilate a pair, we'll take the lowest 2 cells, the lowest cell of each color, black and white. Let's say the white one's lower. So we want to move the black cell to the white cell. Before we do that, we'll move the lowest cell on the board, which is this lowest white cell, down once more. We'll move it down. So now it is strictly lower than every other cell, and it has a 2-row margin. So the next lowest cell could be 2 rows above it. It won't be 1 row above it. So now we will not run into the same issue we had earlier. Because what was the issue we had earlier? That was that if we didn't make any down moves when we were getting the black to the white, we might have issues on moving left or right. But if we ended up needing to make a down move, then if we started with the lowest black cell on the grid and we moved it down 2 cells, it would be far enough away from every other black cell that none of those would get in the way. So if we move this white cell down here now, if we've moved this white cell that we're looking for down, then we'll definitely need at least one down move for the black cell to try and reach the white cell. So if we do the down moves first that we need, then there won't be any black cells in the way. So we can just move right freely and cancel them. In conclusion, how do we annihilate cells? How do we annihilate a pair of cells? Well, let's say we have this starting grid. Well, we have cells in the second row from the top, but let's ignore that. Let's assume there are more rows above. We ensure at the beginning that the bottom 4 rows of the grid are empty. If we ever want to cancel a pair, we do this. We take the bottommost white cell and the bottommost black cell. So those are these 2 in this case. Then whichever one of those is lower down, making it the lowest cell in the grid, the entire grid, we move it down once more by 2 cells, like this. So now it's by far the lowest, by at least 2 rows. Now we take the lowest black cell in the grid, and we try and move it towards the lowest white cell to cancel with it. If we reach any other white cells on the way, we can just annihilate with those instead. So in this case, we're already next to a white cell, so we can't move down. So let's just annihilate. So in that case, we've just cancelled a pair. We've just annihilated a pair. And then if we want to do it again, we repeat. So we take the lowest white cell, and the lowest black cell, and we try and bring the black cell towards it. Now, we have to be careful here because we don't want to move this white cell down again. So we don't want to repeat taking the lowest white cell, taking the lowest black cell, moving whichever one's lower down already, further down by one step. We don't want to always repeat that, because in this case, look what happened. We just cancelled these two. We don't want to move this cell down further because of that for the next cancel. So if we just keep moving this down before each cancel, we'll fall off the end of the board, because now we'll try and cancel this pair, try and bring this cell down to that cell, but again we hit another white cell on the way, so we just cancelled those two instead. And then we try and move this cell down again, but we're falling off the end of the board. That's not what we want to do. So the way we started was we move this cell down by 2 and try and get the lowest black cell to it. But if that lowest black cell was stopped by something, we cancel those two and then we take a different black cell and just keep going. So until this cell is cancelled, we don't want to move this cell down again, because it now might be in the bottom 4 rows, and we don't want to keep going. It's far enough down for it to be the most extreme cell. So now let's keep going. So we take this cell, try and cancel it with the lowest white cell. We move it down. Again, we've hit a different white cell, so we just cancel it with this. Again, we take the lowest black cell, we move it down, keep moving it down. Again, ignore the fact that we're close on the right here. Let's just assume we have more rows on each side. Keep moving it, more columns, keep moving it down, and now we move it left. So that's the strategy, and we've shown that that'll work. And then we cancel. Now we have only one color cell left. But since we have more than 2, we have at least 3, we'll expand one of them and repeat the cancelling. So in this case, we'd end up cancelling these, and then end up cancelling these, let's say. And this is the final layout of the grid. So that is the idea for the solution. That's taken a while to explain, but there are a lot of details here. So let's now go through the code. So this is it. This is the code. It's pretty long. I have a lot of functions here closed down. So I'll talk you through the main function first, I think. Just give you an idea of what everything's doing, and then we'll go through the functions at the top. So this is just input-output. This is inputting everything and printing the answer, because you can easily calculate the answer, i.e. the smallest number of cells you can reach at the end, just from the number of cells of each parity at the start. Like I said, it's the difference mod 5. Although if that's 3 or 4, we want to take 1 or 2 instead, respectively. So we can easily calculate that from the answer. Then this part of the code moves everything up, like I said, creating those bottom 4 rows of the grid, making those bottom 4 rows of the grid empty, creating that space. So we're just checking that the bottom 4 rows are empty. And then we have this while loop, which is the main part of the code, which says while we have both white cells and black cells, while we have both colors, or we have strictly more than 2 cells, in either case, we have to keep going. We have to do something. So if we have both types of cells, then we can cancel a pair. If we don't, then we expand something. So this is the main code of the function. We'll come back to this in slightly more detail in a bit. Okay, so now let's just quickly go through these functions. So n is the size of the grid, that's 1024. This is just a 2-dimensional grid of booleans, just representing whether or not each cell is filled. This is the number of cells of each parity. These sorted is, I have 2 sets of the coordinates of cells. So I have a set of all the coordinates of cells sorted by X and then by sorted by row and then by column. And there are two of them because I have one for each parity. So I have all the black cells and all the white cells separate. And then this I'll get to in a minute. So what's going on here? First of all, I'd like to point out beforehand that X and Y might not be what you expect here. X is the row and Y is the column. And the top left cell is 0, 0. So I have a few functions here, add and remove initially, that are pretty simple. Add sets the value in this grid to true, adds the coordinates to the respective sorted set based on what the parity is, and adds one to the count of that parity. Remove does the opposite. Sets it to false, erases it, subtracts 1. Now we have annihilate. This is the function I call when I want to erase a pair of cells, when I want to annihilate a pair of cells, and it does the printing that I need as well. So if I annihilate a cell, and this boolean is the direction, so either to the right or down, then, well, it makes relevant checks, makes sure that that cell actually exists, is occupied, I mean, and then depending on the direction, it removes both the cells that it needs to remove and prints what it needs to print. So that's annihilate. I've overloaded this annihilate function so that I can call it just with two cells, the coordinates of two cells. It makes sure that that's a valid move, and then it calls the other annihilate function. Clean is a function that goes through the entire grid, and just any pairs of cells that are already adjacent that it can find, just annihilates them, just to make sure that there are no adjacent pairs of cells on the grid. This, I only do this once, so it doesn't have to be particularly efficient. I don't even remember if it's strictly necessary in this solution. But yeah, you go through the entire grid, and this is pretty simple. It's just go through all the cells and check if you can annihilate anything. Expand is the other move, other than annihilate, that we're given in the question, right? So you have to remove the cell XY, and then add all the four surrounding cells around it and print this. And I'm making, again, all the necessary checks beforehand to make sure that this is a valid move, a legal move. Now we're getting to the more interesting functions. So move 2. Move 2 takes a cell, the coordinates of a cell, and a direction, and moves two cells in that direction. So like we were doing earlier, it just uses 5 moves to move that cell 2 slots in a certain direction. And yeah, that involves 2 expand moves and 3 annihilate moves. Depending on the direction, those will be different. So there are 4 possible ways you can call move 2. Say dx1, dy0, or all the other ways. It also makes sure, does the relevant checks as well. So can move 2 is a Boolean function that checks everything sufficient, that checks everything that needs to be checked to make sure that you can move 2 in that direction. Now we have comfortably in. Comfortably in is just a simple function to make sure, to check that a cell is not in the outer 2 layers of the grid. So it checks that a cell is one of these cells and not the outer 2 layers. Occupied surrounding takes a cell and returns any cell out of the 4 adjacent cells to it, returns any of those cells that are occupied. And if none of those cells are occupied, it just returns -1, -1. And finally, cancel pair. This is the This is the interesting function. This is the juicy function. So what does it do? It takes 2 points, A and B, 2 cells, which are the lowest white cell and the lowest black cell respectively. It checks whichever one's lower out of the two. And so we end up having B, point B, XB, YB, being the lower point. So that's the lowest point in the entire grid. And then A is the lowest point of the opposite color. So we move B even further down by 2 slots with the move 2 function. So we move B even further down once by 2 spots. And again, we only do this conditionally. If we've already moved B down by 2 on the previous go, so let me just explain this one more time. Let's say we have this situation where we want to annihilate. So we take the lowest black cell and the lowest white cell. We move the lowest black cell down by 2, like this. And then we try and move the lowest white cell down to annihilate with it. But hey, we can't move this white cell because this black cell's in the way. So we just annihilate the pair. And then we repeat, right? We take the lowest black cell and the lowest white cell. We move the lower one of the two further down by 2. We don't want to do this here. We don't want to do that again because we've already moved this black cell down by 2. So we have what we need. It'll be far lower than everything else in the grid. But we don't want to keep moving it down because it might fall off the grid. So that's what this if is doing. If we've already moved this point, this cell B down, so that it's further than everything else, we won't do this. But if we haven't done that, then we'll move it down and we'll add it to this set of cells that we've moved down. So that's what this up here was that I skipped earlier. And then while then A and B are not adjacent, we'll move A vertically down until it's close enough to B, until it's at least on the row before B, and then if it is, then we'll start moving it horizontally towards B. So if we can make this move, whether it's vertical or horizontal, then we'll make that move on A. Otherwise, there's something in our way, and we've proved on paper, well, if this can be called paper, we've proved on paper that if there is something in the way, it cannot be the same color cell as A. So it's the opposite color cell, which means we can annihilate them. So we'll annihilate that pair using the occupied surrounding function. We'll just take one of the cells around it that are occupied, because there is such a cell, and we'll annihilate them. So if we get through all of these moves and nothing gets in our way, then we'll annihilate with B. So we'll annihilate A either with something on the way or with B. So that's cancel pair. That's what that does. And now returning to the main function, we can see how it works. We can see initially it inputs all the cells, uses the add function to add them to the grid, prints the answer, cleans it up so that we don't have any adjacent pairs. Then I'll skip this line for a minute. Moves everything up once so that the bottom 4 rows are empty. And it does this pretty simply. It starts from the top and starts moving everything up as long as they're not too close to the boundary. So just as long as the top 2 rows remain empty, it moves everything up if it can, right? As long as the cell doesn't enter the top 2 rows or collide with another cell, it moves all the cells up. And the bottom 4 rows will definitely be empty after this because of the sparsity of the grid. And so now the last 4 rows of the grid should be empty. And then we're doing this, like I explained. So while we should make a move to improve our position. So either because we have both colors, or because we have strictly more than two cells. We cancel a pair if we can, otherwise we expand something. We expand anything we want, really. So that's the solution. This line here is because of this. Is because there should be no additional manipulations after reaching the minimum. Because of that, I've added this line. So if there's only one color of cell, and there are at most two of that color. So if we're already at the minimum after we've cleaned the board, then we just stop, because we don't want to do this moving everything up if we are already in the optimal position, because we're told not to do that. But if we're not in the optimal position at this point, then this moving definitely won't affect that. It just moves everything. And then here, while we're not in the optimal position, we're making moves, so we'll definitely stop once we've reached the optimal position. So that's the solution. That is the solution. So yeah, that's the thing. That's my solution. It was an interesting problem. Quite a lot of details. Took me a while to explain. Well, it might also just be that I'm bad at explaining. Probably a combination of the two. But yeah, that's the thing. It was an interesting problem. Quite implementation heavy, or at least my solution is, compared to the other problems at least. But I haven't seen any other solutions to this, so there might well be an easier way of annihilating pairs. So that would be interesting to see. If you have something, drop it in the comments section below, and I'd be happy to take a look. So the initial observation of this problem of moving a cell to spaces was probably the easiest big observation to make out of all four of the problems in this problem set. Although, even though it took me the longest personally to work out, so it took me longer to realize that than to solve each of the other three problems. But yeah, especially if you're using the animation, if you're playing around with it, at some point you'll probably stumble across that observation, if you work with it long enough. But I think the difficulty in this problem comes after that, once you have a vague idea of what you're doing in terms of cancelling pairs of cells, but you have to work out exactly how you're doing that and then implement it. And yeah, so this problem wasn't solved in the contest. No solutions. A few attempts. Some people did attempt it, but yeah, no solves. I'm not too surprised that this was the least solved problem because of the implementation, unless there's a much easier solution. It took me 2 hours to write. Fun fact, I was actually writing it during the contest because I was, well, helping out. As I said, I gave feedback on the problems before the contest, so I was there helping out as well. And during the contest, I had 5 hours to kill, so I implemented this, and it took me around 2 hours to write. So yeah, that's the thing. Thanks for watching. As usual, I'll put my code in the description. I will put a link to this animation tool in the description as well. And I'll put a link, wait, I'm not sharing my screen. Whatever. So thanks for watching. I'll put a link, as usual, to my code in the description down below. I'll also put a link to this animation tool in the description. And I'll put a link to the playlist of all 4 videos from this year's bio, so you can look at the other solutions. So yeah, thanks for watching, and I'll see you in the next one.